It starts with the notion of an elliptic curve, which is defined by a formula that has a quadratic y term and a cubic x term, and then it can have some other terms in the polynomial. If we plot an elliptic curve in the 2D plane, then it has usually this sort of sideways omega shape. It can also have discontinuities like this, where there's a kind of egg shape on one part and a hill to the side of the egg shape. But usually when we try to picture these and explain what they do, we draw it in this omega shape. So what does this curve do for us? It turns out that elliptic curves have the property that if you pick 2 points on the curve and draw a line through those 2 points, you're always going to get one other point in the curve. Always, as long as the 2 points P and Q are not lined up vertically on the same point on the x-axis, but otherwise you're going to hit a third point like R. If P and Q are exactly the same, then we define drawing the line through that one point as being a tangent of the curve, and again this property will still hold. So we can have any PQ, even the same but otherwise not at the same x-coordinate. Now what we're going to do with this fact is, given a P and a Q, we will find an R, and then we will use not R, but its reflection over the x-axis, down here. And this operation of drawing a line from P through Q to the R, and then flipping over it, we're going to call that multiplication, because it corresponds to multiplication in a field in the abstract algebra sense. We're going to draw this kind of multiplication as a dot operator. So if we start with some point P, and we dot P with itself, that will lead us to some other point on the elliptic curve. Here we've taken the tangent to P on the curve, and we hit this other point right here, and then flipped it over the x-axis to get that P dot P below. We keep going by multiplying again with the P that we started from. So that is this new point, which is P squared, times P. We draw the line and find the new intersecting point, flip over the x-axis, and that gives us P to the third, because it was P squared times P. And then we multiply P to the third by P to get P to the fourth here, P to the fourth times P to get P to the fifth, and so on. In general, we're interested in the nth power of P, with the notion of power derived from our dot notion of multiplication. This is really just an intuition for what's going on, because we're using the field R of real numbers here. When we compute with these for cryptographic purposes, we're actually going to use a discrete finite field with modulo integers. So a different kind of math, but the same intuition is behind it. A further advantage of the finite field, though, is that it turns out you can take n steps to get to P to the nth power, that is P dotted with itself n times. You can do that very quickly, it turns out. But here's the kind of property we want. If you just start with Pn, even if you know the starting point P, figuring out what the n was that got you to that point Pn isn't feasible.